Hello everyone, welcome to the video number 10 of this video series Understanding FEA Concepts with 1D example. Okay, today we are going to see different types of elements. Okay, uh, so I highly encourage you people to check all the previous 9 videos. Okay, and I am sure that by going through those 9 videos, you will have clear understanding, fundamental understanding of FEA concepts. Okay, I have tried to explain each and every concepts uh, with possibly taken example. Okay, and I am sure you will get very much clarification. Okay, with this let's start this particular lecture. Okay, before going into different types of element, I just want to quickly recap our previous 9 videos in 2 minutes. Okay, so we started with strong form, which is nothing but partial differential equation. Okay, we derived weighted residual form from the weighted strong form. In particularly, we discussed about Galerkin weighted residual. So Galerkin suggested idea that weighting function and trial function uh, can be a same. Okay, that means we use the same shape functions for weighting and trial functions. Then from weighted residual method, we have derived weak form of the strong form. Okay, in weak form, we have uh, reduced one order. Okay, that means we had a u double dash in strong form. Uh, Here in weak form, it is a u dash. That means the continuity demand in weak form was reduced by one order. Okay, then from weak form, uh, we can get weak discretized form. Okay, so what we do, we discretize our domain into n number of finite elements. Okay, and we write our weak form as a summation over those n number of finite elements. So that is nothing but weak discretized form. So what we do next, we take particular kth element. Okay, and we derived FEA equations for that particular element using shape functions. So if you remember, we said we will assume the trial function, okay, for solution. So we will assume the trial function using shape function, and using that we have got our FEA characteristic equation for 1D bar element. Okay, and that looks something like this. Element stiffness metric Ke displacement vector is equal to force vector of element. Okay, so this is elements characteristic equations. Okay, once we have a FEA equation for each element, okay, what we do, we perform assembly. Okay, so what we, by performing, we get global system of equations which also look very similar to element characteristic equations. Okay, and in this global system of equations, we apply loads and boundary condition and solve the problem. Okay, so that is a quick recap. So let's dive into our today's topic, different types of elements. So before that, what is element? We have discussed that discretization. By discretization, we get the finite element. Okay, for example, this particular object which has infinite number of points, and when we do discretization or meshing, okay, we get finite number of points or finite elements. Okay, and what we do, we find the solution only at the nodes. Okay, and remaining elsewhere, we interpolate the solution, right, using shape functions. Okay, okay, so we have seen that 1D element, node number 1 and 2, and we find the u1 and u2, and we say solution within element is equal to n1 u1 plus n2 u2. Okay, so here shape functions or interpolation for the solution within element is nothing but linear. Okay, so we did linear interpolation. So we are slowly moving into our types of element discussion. Okay, linear interpolation means linear variation. Okay? Linear variation of solution or displacement. In our case, solution is displacement. Linear variation of displacement within element. Okay, and this is called linear element. Similarly, if we introduce mid-side node also in this element, that means three noded element. Okay, we'll have quadratic interpolation, which is nothing but quadratic variation of our solution within element. So this is called quadratic element. Okay, so having said this, we'll now classify different type of elements. We'll do a classification based on dimensionality of element. Okay, so we'll see classification based on dimensionality of element. So first category of elements is 1D element. Okay, for example, if we have structure something like this, okay, whose one dimension, let's take this length dimension x, okay, is very large compared to other two dimension y and z. Okay, then we can represent this structure as a 1D element. Okay, with only x coordinate. Okay, so what about other two dimensions? We represent that other two dimension as a cross section properties or element properties. Okay, and the x we physically represent. So this is a different. Okay, this we represent as a physical. Okay, and here we represent this two dimension in terms of element property. Okay, and in our first lecture itself we discussed about dimension, if you remember. Okay, so there are two types of dimension. One is uh, dimension of element. Okay, and uh, dimensionality of space, right? So so this is based on element dimensionality. This is 1D element. Okay, now this 1D element based on space dimensionality. Okay, it can be in 1D space. Okay, for example, like this, only x coordinate. Okay, this 1D element can be in 2D space as well. Okay, and similarly it can be in 3D space as well. Okay, so in 1D it has only ux, right? So u1 and u2. If this 1D element is represented in 2D space, okay, then the degree of freedom will become u1x and u1y. So node number 1 x degree of freedom, node number 1 y degree of freedom. Similarly, node number 2 will also have 2 degrees of freedom. And in 3-dimensional space, 3D space, it is degree of freedom is u1x, u1y, u1z. Node number 2 3 degrees of freedom. Okay. So this is a bar element in 1D, 2D and 3D space. So here the degree of freedom is per element is equal to 2. Okay. So 1 degree of freedom for each node. Here 2 degree of freedom for each node. So degree of freedom for entire element is 4. So this element degree of freedom is 6. Okay. So this is a bar about bar element. Okay. I'll just say bar element. Okay. Some people call it truss element also. Then see within 1D element we can also have beam element. Okay. Okay. So beam element is something like this. This is also 1D element. Okay. Other two dimensions are very small compared to length. Okay. So node number 1 and 2 degree of freedom is nothing but vertical displacement. Okay. So we will say v1 and v2, and also it will have rotation degree of freedom. So theta 1 and theta 2. Okay. So this is in 1D space. So 1D space degree of freedom will become degree of freedom is equal to 4. So 2 degrees of freedom for each node. If this same beam element, if it is in 2D space in xy, okay, so degree of freedom will be u1x, u2, u1y and theta 1z. Okay, rotation about out of plane axis. Okay, theta 1z. Similarly, node number 2, u2x, u2y and theta 2z. Similarly, beam element. Okay, so for this degree of freedom is equal to 6, and 1D beam element in 3D space. This is 2D space. So degree of freedom is u1x, u1y, u1z, theta 1x, rotation about 3 axis. Okay, and similarly u2x, u2y, u2z, 3 translation degree of freedom and 3 rotational degree of freedom. So this particular beam element in 3D space degree of freedom for element per element is equal to 12, 6 plus 6. Okay. So what this is the difference between bar element and beam element. Bar element has only translation degree of freedom, whereas beam element has translation plus rotational degree of freedom. Okay. So this is about 1D element. Let's see 2D element now. So second category based on dimensionality of element, 2D element. So when we have structure something like this, okay, okay, let's take this is x dimension, y dimension. So when x and y are very large, sorry, very large compared to thickness direction, let's take z is the thickness. We represent that structure as a 2D element. Okay, so this is 2D element where thickness is element property. Okay, and x and y uh, are modeled physically. Okay? So thickness is element property in terms of element thickness. Okay, so in 2D element, okay, we have seen beam and bar. Similarly, in 2D element also, we will have shell element and 2D solid element. So let's see shell element first. Okay, so it has translation plus rotational degrees of freedom. Okay, okay, so shell elements, so there could be a quad shell element or tria shell element. Okay, four noded shell element and three noded shell element. Okay, in xyz space. So for each node there are three translation plus three rotational degree of freedom. Okay, so if I that means 6 degree of freedom per node. Okay? So if I take degree of freedom per element for quad shell element, it will be 6 into 4 nodes, the 24 degree of freedom. Similarly, degree of freedom per element of tria shell is equal to 6 into 3, okay, 18. Okay, so this is a shell element, uh, and other 2D elements are 2D shell, 2D solid element. Okay, shell element has translation plus rotational. The difference here is 2D solid element has only translational degree of freedom. Okay, so 2D elements, same as shell elements, they are quad also and tria. Okay, quad solid element and tria. So these are represented in 2D space only. Okay, and in terms of degree of freedom, so 2D space means one node degree of freedom per node is 2, right? Ux and uy. So for this element, degree of freedom per element is 4 nodes into 2 degree of freedom per node, so 8 degree of freedom. And tria solid element has 6 into 2 sorry, 3 into 2 is equal to 6 degree of freedom. Now these 2D solid elements, there are further two types of 2D solid elements. Uh, One is plane stress and plane strain. Plane stress and plane strain elements. We are not going to detail, but you can I think you can find it online as well. It's a very easy concept, right? Plane stress, 2D solid elements, and plane strain, 2D solid element. Okay, both will have same degrees of freedom. Okay, ux and uy. So this is on 2D elements. Now these 2D elements, apart from they can also be represented in axisymmetric space. Okay, so that is also another type of 2D elements. uh, so we have also discussed this linear and quadratic elements, right? So all these elements again can be of two types. One is linear, another is quadratic. For example, this bar element in 1D can be linear and quadratic, okay, with three nodes. this also. Similarly, beam element, okay, can be a two noded element or three noded element. If it is a three noded element, okay, so it's a quadratic beam element. Similarly, 2D elements, shell elements can be also linear and quadratic. Okay. Quadratic means one node in each side. Okay, one additional mid side node in each side of the element, edge of the element. Okay, something like this. So next let's see 3D elements. Okay, third classification is 3D element. So we'll only see linear, but this element can be linear and quadratic. Okay, so when XYZ dimensions are comparable, okay, XYZ dimensions are comparable, okay, we represent that structure as a 3D element. Okay, so all three dimensions are modeled physically. So there is only one category of 3D elements, that is 3D solid elements. Okay. And they are always represented in 3D space. Obviously, we cannot represent 3D solid elements in 2D or 1D space. So always 3D space. So in this, there are hex elements. There could be so many elements, okay, shapes, but I'm just discussing very commonly and widely popularly used elements. So this is hex element, okay, which has 8 nodes. Okay, hex 8 nodes. Okay, there is another solid 3D solid element, that is tet element, which is 4 noded. And uh, there is also like wedge elements. Okay, wedge element, which is 6 noded. Okay, and solid elements always has only translation degree of freedom. So it is ux, uy, and uz. Okay, three translation degree of freedom for each node. So for this element, degree of freedom is 3 into 8 nodes, so it is 24. That element degree of freedom per element is 4 into 3, 12. And degree of freedom per element for wedge element is 6 into 3, 18. Okay. So these are linear solid elements. Similarly, they can be quadratic solid elements. Okay. For example, I will just show you only one example. Okay. If I take hex, okay, each node has additional mid-side node. Okay. I'll put it a different color. additional mid-side node. Okay, so hex quadratic element is 20 nodes. So degree of freedom is 60. Okay, similarly tet elements, okay, quadratic tet elements should not be quadratic, otherwise quad element is different. So this is quadratic tet elements. So additional node in each edge. Okay, so this will be a 10 nodes, and degree of freedom for this element is 30. Okay, so this is the end of this particular video, and I hope I was able to give you idea about different types of elements. Okay, so this is like very basic classification. Apart from this, there could be many other element types. Okay, but these are the widely used element, okay, that I have tried to discuss. Okay, so this is not the complete note that this is not a complete list of elements. Okay, so thank you guys.